We want to now look at something we call simple harmonic motion. Now, simple harmonic motion is described as a special case of motion. The particle moves backwards and forwards along a line, such that its acceleration at any instant varies as its displacement from a fixed point. What does it mean? Well, imagine a few things. Imagine a pendulum. Think about the motion of a pendulum, how it starts at one spot, moves across, slows, stops, and comes back. And it keeps moving in that motion. Now, if we plotted that, that would look like a curve that starts to look like that. Now, hopefully you're looking at that going, wait on, that looks like a sine curve or a cos curve. You would be exactly right. A sine wave, a cosine wave is in simple harmonic motion. Now, we can prove that something's in simple harmonic motion by doing something very easy. We start with our position in terms of x in terms of t, get down to the acceleration, d squared x dt squared. If you can put your acceleration into this form, minus n squared x, so some number can be factorized out. We factorize a negative, factorize some number out, and we're left with the position function. Then the particle must move in simple harmonic motion, because that's what it means. Acceleration at any instant varies as its displacement from a fixed point. So that statement there allows it to vary as its displacement from a fixed point. So it's related to its displacement. So if you look at the negative, it's obviously working in the opposite direction than what the position is at the time. And it's proportional as well, because it's n squared. So it must be some sort of multiplication variable, whether it's larger or smaller. That depends on the value of n in the function, because n starts to working with the period of the function as well. So if something's in simple harmonic motion, it takes one of these forms. As we said, it's going to be a cos curve, it's going to be a sine curve, or it could be a combination of both. That's one where it's a little bit different. We get a combination of both there. So obviously we know these curves from what we did in the 2 unit, and so we know how to draw those. And so it shouldn't be too hard to play around with something in simple harmonic motion. It's really an idea of getting the idea of what the motion's doing. So for example, in this one we've got simple harmonic motion. It's got a displacement of x is equal to 2 cos t. Well, what does the graph of that one look like? Well, we know how to draw a cos curve. We know that amplitude of 2, period of 2 pi, so that's pretty easy. The equation of the velocity of the particle, well, to get the equation of the velocity, we differentiate 2 cos t, we get minus 2 sin t. Graphing that one up, well, again, it's a sine curve that starts at 0, has a period of 2 pi, has an amplitude of 2. And because it's negative, it moves in the negative direction first. Then C, find the equation and sketch the graph of the acceleration of the particle. So there's our acceleration. And so we've got minus 2 cos 2t. So what does that look like? Well, basically it's going to be the same as our position, because we can write it as minus 1 squared times 2 cos t, and n was 1 in this case, so it's in minus n squared t, so it is in simple harmonic motion. Well, we were told it was, but there's our proof that it was, and that's what our curve starts to look like. So it varies with the position function, which was 2 cos t, but it's also acting in the opposite direction, and we can see that when we put all three graphs together. When 2 cos t is in the positive direction, then the acceleration is in the negative direction. So as we get x being negative, acceleration starts to be positive. So you can see there, because it's negative, there it's going to be opposite every time. So they're going to be in the opposite quadrants every time there. Notice about our velocity. So our velocity is negative to start off with, and that's because it's going to be a situation where the curve starts here from rest. Sorry, it doesn't start there from rest. It does start there from rest because our velocity is 0, and it's reached its maximum value out there at 2, so it must be at rest, and then it's moving in the it's moving towards the origin. So because it's moving towards the origin, then the velocity is negative, and our acceleration is increasing until it gets to a particular point. So notice when our velocity is 0, our acceleration is at a maximum type of value, but even though it's in a negative direction. So velocity starts to increase and it's positive now. So it starts to get to a point where our acceleration is starting to become 0. So our velocity is at its highest point there. Sorry, acceleration. So we've moved ahead of ourselves here. Our velocity starts to get back to 0, and our acceleration's at its highest point. Notice, because velocity is 0, it's going to turn and move in the other direction because the acceleration's starting to change again. So that keeps going on. So you're looking at the idea of what's our relationship between the acceleration, the position, and the velocity at all those particular times. Again, think about a pendulum. Think about how it's moving there. So when it stops and turns and goes in the other direction, that's when our velocity is 0, because something stops moving, its velocity is 0. When it gets to its middle position, so when x is at its middle position, and 0 at this case, our velocity is at its fastest. It comes through and it's at its middle point, and it's going at its fastest in either direction. So you can see velocity is greatest there when the position is at 0. But also at that point, our acceleration is 0 because it's dragged it towards the center, and then it starts to move off in the other direction, but it starts to drag it back towards the center each time. The acceleration always is trying to drag it towards the center, and then it takes off in the other direction, and then it starts to try and drag it back towards the center. That's what simple harmonic motion does for us. So there's an idea. Hopefully you're getting the idea of simple harmonic motion. On our Ed Canvas page, I've included a few GIFs, so a few little diagrams from different web pages and a web page as well, that allows you to have a look at some ideas of things that attract simple harmonic motion, or in some simple harmonic motion. So have a look at those to get an idea of what type of things we're looking at, and the type of, and also you can see the type of motion we're talking about, like waves, springs, tidal waves. It's sort of not great example, but we can try and adapt something towards it because they are in a wave motion as such, with a sine or a cos curve there, and we're going to try and adapt it. But and also the pendulum is a classic one as well. So have a look at some of those, and hopefully we're getting a better ideas. Next videos we'll have a look at some more questions dealing with simple harmonic motion.